Okay, so the next talk is given by Luca Iliesiu, and he will talk about from statistical mechanics to microstate counting for extremal and near-extremal black holes.
Thank you very much for the invitation. It's great to be here. So today I'll be telling you about how to go from the statistical mechanics to microstate counting for extremal and near-extremal black holes. And this is work to appear with Joaquin Turiachi and Samir Murthy, but throughout the talk I'll also reference a number of past works involving these authors. So in the past couple of years, a tremendous amount of progress has been made in understanding how the gravitational path integral for black holes observables reproduces various features of conventional quantum mechanical systems. And to make progress in this direction, I want to answer, using the gravitational path integral, 3 related questions for the special case of extremal and near-extremal black holes. So a question that one might want to ask in any quantum mechanical system is, what's the energy gap above its ground state? So for my question number 1, I want to ask the equivalent question for black holes in a sector of fixed charge. Oh, someone's in front of the projector. So to give you a prior for what people believed about what this energy gap is, it's a well-known fact that as the temperature of a near-extremal black hole is lowered, breakdown of thermodynamic occurs where the black hole doesn't have sufficient energy to radiate even a single Hawking quantum. And it has long been speculated that that energy scale actually coincides with a gap scale, and that speculation was reinforced by various string theory constructions. And since you'll encounter this quantity in a couple of slides as well, I just want to tell you that for Reinstein-Nordstrom black holes in flat space, the non-supersymmetric black holes, the breakdown of thermodynamic occurs when the temperature is given by 1 over the charge of the black hole to the 3rd power. If this gap truly exists, then we would expect that all extremal black holes have a degeneracy that's proportional to e to the area. However, for non-supersymmetric black holes, there's no symmetry principle that should be protecting that degeneracy. So in light of that, for my question number 2, I want to ask, are all extremal black hole states truly degenerate? Finally, if we find examples from the gravitational path integrals that actually have a degeneracy, then it better be that this degeneracy is an integer, like in a UV completion of gravity. So as my final question, I want to ask, can the gravitational path integral reproduce a microstate count, including the integerness of such a count? And I'll discuss specific example of microstate counting. So to start, I just want to briefly review what the gravitational path integral seemingly tells us for extremal black holes. So as many of you might know, there is a famous computation by Sen and collaborators in which they computed the quantum corrections to the extremal entropy for a variety of black holes. And the answer always takes the following form, that the degeneracy is given by e to the S0, where S0 is the area, plus a logarithmic correction in the area multiplied by an order 1 number. So this number c explicitly depends on the field content in the gravitational theory. But regardless of what c is and whether the theory is supersymmetric or non-supersymmetric, this result suggests that even accounting for quantum corrections, we get a very large degeneracy, which, as I said, is a bit suspicious for non-supersymmetric cases. So to answer my question number 1 and number 2 for both non-supersymmetric, this is what we'll study first, and supersymmetric extremal black holes, study second, I want to quickly review this computation. So how this computation is done is that one considers an extremal black hole background, which in the near horizon geometry is given by ADS 2 times S2 with equal radii. And one takes all the fields in this background and expands them into a classical piece and into a quantum fluctuation. Afterwards, one expands these quantum fluctuations into modes and expands the action to quadratic order in these modes and tries to integrate out these modes. So there's 2 types of modes that are important. First, there are modes with non-zero eigenvalue. And their one-loop determinant produces a fairly unambiguous power of S naught that can be calculated using heat kernel methods. So this C non-zero number is just something that depends on the field content of the theory. And I'll tell you in a bit what it is. However, there are more problematic modes, which is that the action expanded to quadratic order has zero modes, and in fact, this is not only an infinitesimal statement, these zero modes survive to all orders. So what are these zero modes? These zero modes are given by large diffeomorphisms and large gauge transformations of the fields that I have in my theory. So to make things concrete, for Reinster-Nordstrom black holes in the canonical ensemble, there is only a single zero mode that actually affects the computation in a relevant way, which are the large diffeomorphisms of the metric. So to tell you exactly what the zero mode does, consider an asymptotic boundary that's very far away from the center of ADS that has a constant extrinsic curvature. If I implement this fluctuation, the space-time is mapped to, this curve is mapped to a curve that no longer has constant extrinsic curvature. So it just means that it doesn't vanish, this fluctuation doesn't vanish at asymptotic infinity. And at this point, there are probably two communities in the audience that recognize this mode. The first are those that computed the log corrections for these black holes. And the second are those that study JT gravity that might intuitively recognize this mode as the Schwarzian mode. And I want to make a connection between these two communities by explaining how things work. So one can integrate over this zero mode, and what Sen and collaborators beautifully do is that they strip this integral over the zero mode of its entire S naught dependence. So in total, the power, this changes the power of S naught in the one loop determinant to be an overall factor C that, as I said before, depends on the exact number of free fields in the original theory. So it depends on the number of free scalars, numbers of free vectors, and number of free fermions. But what's left over is an integral that is independent of S naught over all these large diffeomorphisms that I have to quotient by the space of isometries of my manifold. But this integral has zero weight. So formally, it just gives a divergent volume. And the logic was that since this divergent volume is independent of S naught, and the only scale entering as zero temperature is S naught, then we can just drop this guy. However, the important question is whether this divergent volume, when regularized, produces zero, a finite number, or infinity. So in order to make physical sense of this question, we have to compare the partition function at zero temperature, so at extremality, to another partition function in order to get rid of all divergent factors. What I will compare is the partition function at zero temperature to the partition function at finite temperature. And the way in which we can do this is we can do the same computation that Sen did, but instead of starting with an extremal background, we can deform the background to move it near extremality. So this is a temperature-dependent change. And beautifully, the role of this temperature-dependence change is that now all the previous existing zero modes now gain a non-zero weight. So for this reason, since there are no longer zero modes in this new background, I'll call them would-be zero modes. Because they wanted to be, but they couldn't. Okay, so then the partition function of the black hole at finite temperature has two parts. The old part that comes from the massive modes that are not actually that affected by the fact that I changed the background a little bit, that correction is suppressed by 1 over S naught. And the contribution of the would-be zero modes that was previously discarded. And this contribution is given by a path integral over all large diffeomorphisms that I denote by the epsilon, where by just plugging these large diffeomorphisms into the action with the background that I previously mentioned, one recovers the Schwarzian action, whose coupling I wanted to identify from the first slide. This is precisely the scale of the thermodynamic background that Presskill and collaborators suggested in the 90s. And what happens as the temperature of the black hole is lowered is that the coupling of this theory is given by the ratio between this energy scale and the temperature. So as I lower the temperature, this mode of the zero modes becomes very strongly coupled. And this signals the fact that at low temperatures, there is a failure of semi-classical physics because there are modes that, we cannot simply integrate to quadratic order. We have to consider exactly. Now, luckily, in a result of Stanford and Witten, it was showed that this path integral is one loop exact, so it can actually be computed exactly. And the result overall that we get by combining sense computation with the results of Stanford and Witten is, in some sense, the product between the two. There's the old part, which gives the corrections to the overall scale of the density of states. And then there's a temperature-dependent one-loop determinant, as well as a more boring classical correction to the black hole free energy. The important thing to notice is that as the temperature is lowered, the role of this one-loop determinant becomes more and more important, to the point where if I set the temperature to 0, the ratio between the two partition functions that's regularization independent actually goes to 0, which suggests that for non-supersymmetric black holes, there's no degeneracy. And to be a bit more accurate, we can actually constrain this ratio to be non-perturbably small, which means at least that black holes are much, much less degenerate than previously believed. So to get an even better sense of what's happening, we can look at the density of states by simply Laplace transforming this partition function. And starting from large energies, far away from extremality, we see that the classical prediction for the density of states, which I marked with the dotted line, dotted curve, agrees very closely with the density of states, including quantum corrections. But as I lower the temperature and I reach this scale, the two curves start deviating to the point where at extremality, this density of states goes to 0. So to summarize, the answer to my question 1 and question 2 for black holes that have no preserving supersymmetries is that in Einstein-Maxwell theory, there is no gap, at least at the scale that was previously suggested, and no degeneracy. And this can be checked both through a dimensional reduction and through the computation that I just described, in which we just expanded the action to quadratic order and kept track of all the modes. So how about the black holes that preserve supersymmetry at extremality? It better be that the result should be different, because we know, for instance, from computations of Strominger and Wafle, that these black holes do have a degeneracy. So for supersymmetric black holes in both ADS and flat space, although I will focus only on the case of flat space today, the same one-loop computation and accounting for the would-be zero modes gives a wildly different conclusion. The would-be zero modes are now different because I have to integrate over large super diffeomorphisms instead of large diffeomorphisms. But I'll just show you what the density of states is in this case. So this is for black holes in 4D flat space in a theory with more n greater or equal than 2 supergravity. So again, starting from large energies, we see that the classical prediction and the quantum corrected prediction agree. But this time, as we lower the energy of the black hole towards extremality, we see that the density of states precisely vanishes at a scale that was the thermodynamic breakdown scale that people discussed in the 90s. And beautifully, what happens is that the integral over these would-be zero modes produces an exact delta function in the density of states. So this exact delta function is multiplied by the degeneracy previously found by Sen and collaborators. So the answer to question 1 and question 2 in this case is completely different. In supergravity in flat space, there is no gap, and there's a massive degeneracy. And this is consistent with expectations from microstate counting and with the expectations from the stringy construction of the gap. So just to contrast the non-supersymmetric case and supersymmetric cases, the difference between the two can be summarized in these two plots. So the action is always 0 when the temperature is turned on to 0 for these zero modes. but the regularized integrals in the two cases are completely different. In the non-supersymmetric case, it's 0. And with supersymmetry, it's exactly 1. And we'll actually see that there are cases in which the result is slightly different than 1 that will be very important in the upcoming slides. So what we've reproduced can you move? So what we've reproduced so far is the fact that these black holes have an exact degeneracy, and this degeneracy can be probed in various ways, and I think in Juan's talk he'll discuss more about observables related to this degeneracy. But what we haven't reproduced so far is the integerness of this degeneracy. Namely, if I change the quantized charges of the black holes, these numbers won't all be an integer at the same time. So can we do better for extremal supersymmetric black holes and reproduce this degeneracy in a microscopic model? And the microscopic model that I will consider are 1/8 BPS black holes in n = 8 supergravity in 4D flat space. So I'll be very brief in describing the string theory construction. Essentially, like the degeneracy of these black holes has been obtained in a D1, D5 construction and was found to be given by the Fourier coefficients of a weak Jacobi form of weight -2 and index 1. So these weak Jacobi forms depend on two integers, n and l, which we'll recognize as the charges as two of the non-trivial charges of the black hole. And overall, the Fourier coefficients of the weak Jacobi form have the nice property that they don't independently depend on n and l. They depend only on this duality invariant combination between n and l. And this quantity I'll call delta, and we'll identify the relation between delta and the entropy of the black hole. So the important property that we'll use for these Fourier coefficients is that they admit a Rademacher expansion. And this Rademacher expansion is just a sum over integers. It's a convergent sum with successively smaller exponential terms given by this Bessel function. When I expand this Bessel function at large delta, these give me the successively smaller exponential terms. And this Bessel function is multiplied by something called a Kloosterman sum, which is just a sum over some exponential phases that don't grow with delta. This Kloosterman sum doesn't grow with delta, rather it oscillates. So to address question 3, I want to ask if we can reproduce this formula exactly, the Rademacher expansion, by using the gravitational path integral. And a lot of progress has been made in this direction using localization and supergravity by these people. And while, for instance, all the exponential phases in the Rademacher expansion and the exponential growth has been accounted for, people had not yet computed the one-loop determinants either around the leading black hole or around subleading geometries. But we will do this, and I'll describe that in this talk. So to give you some background, how localization works in supergravity is that one starts with a space that's asymptotically AdS2 times S2. We don't know what's in the interior yet. So asymptotically, there is a PSU112 isometry that causes killing spinors and killing vectors to exist locally. And one can choose a killing spinor that generates a supersymmetry that I'll call EQ, such that the square of this supersymmetry is equal to a difference between two U1 generators, one in the AdS2 direction and one in the S2 direction. One then takes the supersymmetry and deforms the supergravity, the initial supergravity action by a Q-exact term. And the nice property of this deformed theory is that its partition function is actually independent of the coupling lambda of the operator that I just added. So I might as well evaluate it at lambda equals infinity, in which case I can simply evaluate the path integral for a saddle point approximation and the one-loop approximation around that saddle point. So the path integral localizes it to a configuration where all fermions are 0, but also Q acting on all physical fermions needs to be 0. So this implies two things. Firstly, it implies that the metric is locally AdS2 times S2 everywhere. Globally, it implies that the only geometries that we should be considering turn out to be the regular ADS2 times S2 geometry and an orbifold of ADS2 times S2. This equation technically implies that this orbifold can have the angle of ADS2 to be anything, but if we want this to actually be a smooth manifold when we include the additional extra dimensions, it turns out that this angle needs to be quantized and equal to 2 pi over c. So the perspective that we'll take is that in the gravitational path integral, we have to sum over all topology, so we'll sum over all these geometries. For all other fields, this equation implies that the fields need to be set to the attractor value, with the exception of all the scalar in the vector supermultiplets that turn out to have an entire localization locus, which we parameterize by these numbers phi I. And I'll just tell you that phi 0 is the scalar in the graviphoton supermultiplet and will play an important role in the calculation. So now what we simply have to do is evaluate the supergravity action on this localization locus and evaluate the one-loop determinant and do the integral. So we have to do an integral over the entire localization locus. And luckily, the supergravity action simplifies drastically when evaluated on the localization locus. There's only two terms that survive, a boundary term and a term that comes from the n=8 prepotential. And luckily, the n=8 prepotential is Strevel level exact. So while you might expect that there's higher derivative corrections that we can't really account for, because things only evaluate to the prepotential, those don't really matter. And there's a one-loop determinant that only turns out to depend on the scale of ADS2 times S2, which is given by phi 0. A similar formula applies to the orbifold geometry, where I now have to integrate over, where now the on-shell action is just scaled by a factor of 1 over c. That's roughly because the volume of the orbifold is smaller. And there's a one-loop determinant that in principle could have a non-trivial c dependence. And there's also a topological term that has been evaluated in the work of these people that turns out to reproduce precisely the Kloosterman sum that appears in the Rademacher expansion. So luckily, in n=8 supergravity, the prepotential that appeared in the action is only quadratic in phi 1 through phi n v, so those fields can be completely integrated out. And what I'm left with is an integral of phi 0, where the missing ingredient is precisely the one-loop determinant that I mentioned previously. So once again, to compute the one-loop determinant, we have to separate it into the contribution of the bulk modes and to the contribution of zero modes. These zero modes turn out to be both zero modes of the supergravity action and zero modes of the QV term. So the same thing that I said earlier also applies when doing localization. And although I don't have time, I will just tell you roughly how we did the computation for the one-loop determinant of the bulk modes, which is that in the n=8 theory, we separated into n=2 supermultiplets that have an off-shell formulation, and we related the one-loop determinant of each supermultiplet to an index and computed that index using the Tiabat fixed point formula. And for each supermultiplet, the expression is a mess. It's a complicated expression in terms of phi 0 and c. However, if I multiply all supermultiplets in n=8 supergravity together, I get an extremely simple answer that's c independent. And we don't really understand why. This is just what the localization computation spits out. Finally, I have to also consider the integral over zero modes, which again are given by the integral over large super diffeomorphisms. But now remember that the ADS2 part had a defect. So this integral actually changes. And importantly, it changes by precisely a factor of 1 over c. And this factor of 1 over phi 0 simply comes by absorbing the phi 0 dependence in the measure of the zero modes. So now we can put all the results together. We have an integral over phi 0, where we now know the one-loop determinant. And this integral reproduces precisely the Rademacher expansion, where we notice that the would-be zero modes played an important role because they gave the right c dependence in the Rademacher expansion. So to answer the question number 3, the partition function at 0 temperature using the path integral precisely reproduces the microscopic degeneracy from string theory. And this is fairly miraculous because this means that you can reproduce an exact integer from the gravitational path integral using localization. Yeah, so just to describe what happens in this sum over degeneracy, for this degeneracies, the sum over topologies is absolutely necessary, a thing that we oftentimes don't know in the gravitational path integral, but is nevertheless under control. And because of that, one could say that we found an exact example of ADS2 holography, since the degeneracy is an exact integer and could have an associated Hilbert space. And I hope there will be many more examples to follow, just due to the fact that we only used n = 2 supersymmetry in order to perform localization, and there's numerous other examples in string theory for which the degeneracy is known. Thank you very much. Any questions?
Yeah, thank you very much for your talk. There are questions.
You're allowed to give me your microphone? Okay, anyway. Thanks, very nice talk. I think I already saw that you flashed some backup slide that I was going to ask you about. Could you tell us a little bit more about the connection to the topological expansion?
Yeah, so there's two connections. So for this continuum in the density of states, the fact that it's a continuum is related to the fact that the topological expansion is not under control. In order to actually find the discretum in this continuum, in principle, we need to have full control over stringy and non-perturbative corrections. The best we can hope for, however, is that we'll get information about the spectral statistics of this continuum by looking at configurations with non-trivial topology, like wormholes. In the case of the degeneracy, I just want to emphasize that the topological expansion is completely under control, both for the index and for the actual degeneracy. And this is because, number one, for all the geometries that we considered, there's a way to show that the index is equal to the degeneracy. But then one might be worried that there are configurations that have zero index but non-zero degeneracies, like, let's say, homogeneous surfaces. But it turns out that they all evaluate to zero in the limit in which the temperature goes to zero. So they don't contribute. And, the fact that we get an integer would have been a little bit in tension if, this specific observable didn't also solve the factorization, that also had a factorization puzzle. Namely, if this observable had non-zero contribution for wormholes, would have been a little bit weird with would have been a little bit in tension with the fact that we got an integer. But luckily, we verified that for all wormholes, the degeneracy actually vanished. The connected component of the degeneracy actually vanishes.
Okay, follow up.
The question was actually simpler than that. From the higher dimensional perspective, it's not clear why you should include topology at all. That I didn't understand.
Why you should include topology at all?
Yeah, usually that's not done. Right?
Well, I think this should be indicative. The fact that we matched an integer by summing over all orbifolds suggests that we should take the sum over topologies in gravity seriously. If we only considered the leading saddle, we wouldn't have reproduced the correct degeneracy. So maybe this should be taken as an indication that we should sum over topologies.
Hey, Luca. So great talk. So the first question I have is that in the Rademacher expansion for the C = 1 case, because the phi minus 2, 1 has just one polar term, you almost get something that looks very, very close to the localization answer. Right? So my question is, does adding these extra, computing these the one-loop determinants in the way you've explained, does that make the answer between localization and number theory converge faster, or
faster than what?
I mean, I don't know, because if you compute C = 2 without these one-loop determinants, the way Atish and others did, would that Does your
So
analysis...
this answer, accounting for the one loop determinant, causes the answer precisely to match with the Rademacher expansion.
already at c equals 1, or?
No, at all C. That's the formula for all C.
Okay.
So like the answer converges and it's just identical to the expression of the Rademacher expansion for the Fourier coefficients of the weight 2 index -1 weak Jacobi.
Minus to 1.
Okay, sorry, weak Jacobi form.
Another question.
Hi, thank you for your talk. So I guess your discussion was in the context of the canonical ensemble with all the charges fixed. As you're surely aware, some of us showed that in, for example, in generic supergravity, near extremal supergravity backgrounds, GT arises universally near the horizon. And as you also showed, I mean, if you take that input from the UV, then doing a Stanford-Witten analysis about this GT gives you the quantum prefactor. But we also showed in some cases that there are, in other ensembles, there are other modes that are at least as important as the Schwarzian. So I was wondering if you have anything to say about some of these other ensembles?
Yeah. Well, we can also actually I didn't have time to go over the details, but in the case of n equal the n equal 4 supergravity path integral. 2D n equal 4 supergravity path integral in the near horizon region, one is forced to actually work in a grand canonical ensemble for the angular momentum. And then afterwards, you do the resulting, you compute the results in grand canonical and take the Laplace transform and get the canonical answer. So what might happen is that in grand canonical, your one loop determinant will be different. You'll end up with a sum over some saddles. But when you Laplace transform it, this is the density of states that you get. So I didn't have time to cover grand canonical, but.
So this story you expect should be identical to...
Yeah, everything is consistent.
I mean, once you have... Sorry, go on.
Yeah, my only comment is what we mean by grand canonical in the near horizon region is a little bit different than what we mean for grand canonical when fixing the holonomy at asymptotic infinity for a black hole. Namely, fixing the holonomy at infinity translates to a slightly different condition at the boundary of ADS2.
Right. That's right, yeah, that's what we have explored. Thanks.
Okay, let's postpone all further questions and let's thank Luca again. So please enjoy your lunch and we reconvene at 2 p.m. sharp.